Okay, so as I mentioned before, today the idea that I had in mind was just to kind of mention like a cute application of this duality stuff to game theory, which is like an important topic. And then that would be the last topic for the exam. And on Monday, then it's kind of like more like kind of like these office hours we have done before. So you can, I'll be here for the entire class if you want to come with any questions. And then Wednesday we would have like the actual exam. Um, this topic is like okay. There are different ways to explain it. Hopefully, I'll explain it in a way that is like digestible enough. So, but yeah, do stop me if it's kind of like a bit confusing. So. Okay, so in game theory, what we're going to talk about is what people call like a zero-sum game. So a zero-sum game is like, it's a game we're playing. It could like the game could be flipping a coin, could be rock, paper, scissors that I had mentioned last time. Any game, a game is basically something that has like potential outcomes, right? And where they're like uh, there will be two players, okay? So we'll have two players. Kind of like I don't know if it is like a tradition in this top in area, but like I'll refer to the players as Alice and Bob. At least those are kind of like the go-to names in computer science and quantum physics and all this stuff. So just like and also I think that is the name that the book uses as well. Okay, so Alice will be called like you'll see why the role player, and I'll call Bob the column player. So the idea is that they're playing a game, and after each round, there will one of the two will win. So, for example, if Alice wins $3, that means that Bob loses $3. That's what makes it zero sum because you're setting up the game so that what one wins, the other gains. Sorry, what one wins, like the other loses, right? Like so, like someone's gains is the other person's loss. So that if Alice wins X amount of dollars, let's call like a certain N dollars, then that is amount. And vice versa. So it's like entirely symmetric. So here's like like an example of a zero-sum game, which is they can be represented by matrices. So this is where like the matrices will come into play. I have like a few here. I wrote this many times just to come up with the best possible way to explain it. So let me find the most recent way to do this. Okay. So the idea is to represent the game by a matrix, which is called the payoff matrix. So you represent the game by a matrix. No, sorry, I'll put the 2 here. Okay, so let me tell you how to interpret this matrix. So again, it's 2 by 2. So the way you should think about it is that there were two choices that each of the players could make, right? So since each player has two choices, 2 times 2 is 4. So there are 4 possible outcomes to the game. So just to make it more concrete, imagine that the game you're playing is that each has a coin that they're allowed to flip, right? So Alice flips her coin, Bob flips his coin, right? So that the potential outcomes are like heads, tails, right? For each of them, right? So like, for example, if I write, like I'll write it like this. Um, so what does that mean? Here, that means like, again, Alice is a role player. So what does this entry means? This means that here, like Alice being the role player played tails, or got like, when she flipped the coin, um, tails, and Bob got heads, right? Right, so because it's H for Bob, Bob is column, so H here, tails for Alice, right? And the interpretation here of this number 1 is that that is the amount that Alice would get paid. So in this round, if they play that way, Alice gets $1. That kind of making sense? Now, for example, let's maybe the one that's a little bit harder to interpret is like the one with the negative one. So what is happening here? So this is like a case where they both played heads, right? And so here they both played heads. And so what does it mean to say that Alice gains -$1? It means that Bob gained the dollar, right? Like, like it's zero sum. So like, someone losses is like the other person's gains. So, you can still kind of like think of it as she won like a negative number, but she winning a negative number means like that's like the amount that Bob actually gained, right? So -$1, which in reality actually means that Bob gained that amount, right? So like, yes.
So why are we saying that, like, no matter, like, whenever the intersection, that's just how much Alice gained?
Yeah, it's kind of like like the way the matrix is being presented is biased because it's kind of like telling you like the results of the game from Alice's point of view, right? If you multiply everything by -1, like if you multiply every entry by -1, that would be Bob's point of view of the game. Like the thing is like if the game is not zero sum, if the game is not zero sum, then like each would have like their own matrix. It's just that in the zero sum game, one matrix is minus the other matrix. So it's kind of like we just keep one of the two, if that makes sense. So yeah, this is all from Alice's point of view. Yes.
Really convention that like the matrix.
Actually, it does change. So I'm following the books convention, like the official textbook. If you go to other places, like it is reversed. So like they would think about it. You have seen it in the other way. Yeah, yeah. Oh no, no, yeah. Definitely, you do have to pay attention to uh everything can like the notation, like if my sense is like it does like very sensitive to which book you're opening, but it's not too bad to adjust like your point of view. But yeah, this is kind of like, but yeah, this kind of the game that so Bob actually gained the dollar, right?
How do we know who's like gaining or losing? Or it's just like.
Oh, look, right, like this is I will always set it up from the perspective of Alice. So it would be kind of like you can think of this as a payoff matrix for Alice. So this is Alice's payoff matrix. Um, the point is like again like the Bob's payoff matrix is just the minus this one, you see. So like you only need to have like one of the two. That's basically it. Is that making sense? Yeah, but like my convention, true, because like sometimes like it's explaining the opposite way. So you do have to decide how do you want to set it up. So I'm setting it up so that like these numbers tell me how much Alice is getting paid after each round.
So if it was for Bob, he would tell us it's for Bob.
I would always do it for Alice. I'm always going to do it for Alice because otherwise, like, I'm ruining people's lives for no good reason. Like, so no, it will always be from Alice's perspective because also like that's like the one that the book does. Um, So like I'm not going like it would be crazy to change it, But yeah, like so don't worry about that part. But yeah, if you're reading other books, everything could be flipped, like the interpretation could be flipped because like they're referring to like the Bob's point of view. But from this perspective, like from this perspective, with respect to this matrix, Alice loves positive numbers and Bob loves negative numbers, right? Like the more negative the number is, kind of like the better it went for Bob. And you like so kind of like that's how you should think about it, like the matrix here. So from this uh, from for this interpretation of M, Alice loves positive numbers. And the larger, the better, right? Like, because that means like in that particular round, she would have gained even more money, right? And Bob loves negative numbers. Okay. But this is game theory because like you want to strategize in a way that's kind of like the best possible way. So like the question, like I'll start like you know like you have to look at it from perspectives. But we will try to be like a rational agent, and I'll tell you what I mean by rationality in a second. Uh, but we would like like the idea is like what if you're Alice, should you try? I mean, maybe flipping a coin. I shouldn't have said flipping a coin right now because if I say flipping a coin, that means kind of like a randomness element that you may think about because you would think, oh, I cannot control that. So maybe think about it more like a switch that can turn on and off in the sense that Alice does have control on which like outcome she wants to play for now. Like actually later, I will randomize it and I'll be like, okay, we'll just going to play the game by luck. But right now, think about the game as being deterministic, where like Alice can actually choose, like whether like I'll put it like I'll use actually the letters like UP for up down. No, so like UD, like kind of like a like kind of like up and down, like it's kind of like an arrow that she could point up or down. So like that way kind of feels more like in her control. Because if I say a coin has like this element of randomness attached to it, and I don't want you to think about it in that way right now. So like sorry about that. Like I correct myself because yeah. Like so is it like we're playing right now a deterministic game where you just choose like whatever strategy you want to choose. Uh, so Bob is playing you. Okay. So, but okay, so again, like let's try to analyze. So let's try to analyze the game from Alice's perspective, and then we'll kind of like do the same from Bob's point of view. Okay, so I'll kind of copy paste like the matrix a couple of times because it's useful to write it, you know. Okay, so from her perspective, what happens? Okay, like again, we have to be slow, but what happens if Bob I'm Alice. I don't know what Bob is going to choose. So what happens if Bob chooses column one, which would be like up in this case, right? So if Bob chooses column one, I'll put in parentheses that would be the outcome that I'm calling up, right? Okay. So this is like the choice that Bob is going to make, right? So the potential like outcomes, in this case would be in this column, right? And Alice loves positive numbers, right? So she being rational, if you're a rational agent, if you think that Bob is going to choose up, you will choose down, right? Is that making sense? So Alice chooses, which is row two, right? And here the outcome, like what would happen in this particular round would have been that Alice ends up with +1, right? Okay. Now, what happens if, again, we're Alice, we're exploring all the cases. So what happens if Bob chooses um column two, right? And by column two, I mean that he decides to play option D, right? So if Bob chooses column two, again, Alice likes positive numbers, so she'll choose D as well because that would give you three, which is the highest number here that she could gain, right? So Alice chooses D, which is row two. So in this particular round, um, like if the game had gone that way, she would have ended up with +$2. Is that making sense so far, so good? Okay. So you see, like there's certain assumptions of rationality being thrown in. Like first, like that she would want to try to choose like the option that gives her the most money, which is natural. And also, okay, so you had these two perspectives, and there's also like another sense of rationality which is kind of like I'll be risk averse. So if I'm Alice, I want to know what is the worst possible scenario, right, of these two outcomes. So like the worst case scenario would be where I just gain +$1. Okay, so of like these two possibilities, I know for sure like the worst I could end up being doing is like $1. So the worst case scenario for Alice is ending up with $1. Is like +$1. So I'll kind of like underlie where that happened. So the +1 case happens here, right? Yes.
For the second one, if option is column two, alpha two, go to literally plus two.
Oh, yeah. So yes, you're good. Yeah, sorry. Oops. Yeah, yeah. Thank you. Thank you. It doesn't change what I just said, but yeah. Yes. Like I don't know why I said +2. Thank you. Thank you. Ooh. By the way, as a historical like throwback, like so a lot of this stuff was developed kind of like in the 50s, 60s during the Cold War, and the US military spent a lot of energy, like, the same theory, because like the idea is like if like the mutually assured destruction, if the Soviets had like nuclear bombs and the Americans have nuclear bombs, like kind of here you're trying to look for the worst case scenario because like, of course, like someone could like bombard first and then you win, but like, you have to look at what would be the worst possible thing that could happen. And if you're willing to assume that risk, then you would proceed, right? But it's kind of like, so you should think of the game maybe as something that you're trying to really see not happen to see like how bad it can really get. So in the case of nuclear weapons, it's kind of clear, like, what could happen. And this is kind of like this mutually assured destruction policy that they developed. But so there was a lot of like actual investment in game theory, like for those historical reasons. And there's like where this prisoner's dilemma comes from that probably you have heard of. So there's a lot of like interesting stuff that like happens here. Of course, this is kind of like the most baby version of a game theory because it's zero sum, only two players. Like you can imagine making this super complicated with more players involved. Like, like there's so many generalizations of this, but it's kind of like a small case that is easy to understand and it's related to this duality of linear algebra, which is kind of like the cool thing. And you'll see why in a moment. Okay, perfect. And now let me just, so this worst case scenario for Alice happened in column one, row two. So this is where like the worst case scenario happened for Alice. So I'll just also put like a circle around it just to know what was like this worst outcome possible. Now let's just look at exactly the same situation, but from Bob's point of view. So in this game theory, you always have to look at everything from each player's perspective. So So again, you're Bob, and you have to think, okay, what would Alice like to do? So again, Alice is role player, so she will choose like something in these rows, right? So imagine that Alice chooses you. So if Alice chooses you, which choosing you is like just saying row one, right? So imagine Alice made a choice here, right? Again, Bob works the other way. Bob loves negative numbers, right? Or the smaller numbers possible. So Bob would like to choose you, like he would choose column one because that's where he would get a negative one. So Bob chooses you. And like, again, we're looking at everything kind of like of what ended up happening with Alice. So Alice would end up with negative one or like, which is the same as saying that Bob ends up with plus one, like, you know. But I'll put both here because like that's how you should interpret that. Um, and then again, choosing you would have been column one. Okay, and then let's go through the second option where if Alice chooses um, if Alice chooses D, if Alice chooses D, which would have been row two, right? Um, if Alice chooses D, which is row two, again, what is Bob's preference? Bob loves negative numbers. Here, he doesn't have a negative number to choose from, so he has to go as low as possible, right? Because to minimize Alice's gain. So Bob would choose one, okay? So, or meaning column one. So Bob chooses column one, which is up, right? And so if we do that, so where he chose column one, so that means that Alice ends up with plus one and Bob ends up with negative one. So far, so good. Is that making sense? How are we doing? Okay, and again, being rational, you would just want to say, what's my risk here? So what is my case perspective if I'm Bob? You know, my worst case perspective, like that's why I'm putting like also things from Bob's perspective to make it more clear. The worst case scenario for Bob is this one because in this scenario he lost $1, right? In the other one he would have gained. So for Bob, the worst case scenario is what? It would have been you know, like when the last case where he lost $1. So where does that happen? It happens right here. Okay. This is where Bob's worst case scenario happens. Is that making sense? Now, something curious happens here because if you notice, I'm singling out exactly the same matrix entry as before. So this is a game where both players' worst case scenario happens in exactly the same spot. You see? And that is what is called like an equilibrium solution or like an equilibrium situation because kind of like the worst possible outcome is the same for both people. Like, you know, it's sometimes called like, I guess, like a Nash equilibrium. You know, like, have you heard like there's this movie, John, like A Beautiful Mind with John Nash. He was like a famous mathematician at Princeton University. If you are interested about, like, he developed a lot of this like game theory stuff, and there's like this Nash equilibrium, which is used in economics and all this other stuff. So if someone wants to check out that movie, you should. Like, if you want to, I mean, in fact, a lot of this stuff happened near like our area because Princeton is so close to like where we are. So like, um, so notice here, um, the worst case scenario. and the same entry for both Bob and Alice. Okay. Uh, the thing is that you like if you had to take a guess, you probably would believe you would think maybe it's possible that that wouldn't be the case in general, right? Like if you were to just like imagine choosing like a random matrix for the payoffs, it would be pretty amazing if like the worst case scenarios always happen to agree. So in fact, like that is not the case. Like it's very easy. Like let me write one where like the worst case scenarios would happen at different outcomes. Um, And I won't go through all the details because, like kind of like the analysis, it's not, as you can see, it's not too complicated, but you also have to be careful, you know. Okay, so if you take another example, if you take something like this, then, right, so in this case, I think this should be the worst case, where the worst case scenario for Alice happens. And the other one, the worst case scenario for Bob, happens at the 3, if I'm not mistaken. This is where the worst case scenario for Bob would occur. Okay. And again, it's not too bad to work it out if you want to try it. Like you just do exactly the same analysis that I just was doing here. So, it's kind of like unfortunate because it's kind of like nice if it happens to coincide. So you kind of try to relax the problem, and just like you randomize. How do you relax the problem? You randomize it. So like now you're going to think that kind of like Alice and Bob play the game at random, like by making their choices at random. Okay, and that's where like the coin comes in, like which is like a better like that's why I told you like let's think about up down for now. So like imagine like Alice is going to choose to play the game by like, by like let's say maybe choosing with probability 1/3 to choose up and then probability 2/3 to choose down, and same with buff. Okay, could choose probability 20% to play up or probability 80% to play down, right? So the question if is once you allow them to play the game at random, is there kind of like an ideal choice of probabilities, that they could choose to kind of like play it in an optimal sense? Okay, so now Alice and Bob will randomize their strategies in the sense that so Alice is going to be, how I'm going to put it like this. I'll use the vector notation. So x1 and x2. So x1, this is going to be the probability. She chooses, uh, what am I calling them here? Up. Okay. She chooses option 1, and this will be the probability. She chooses D. And same with Bob. So Bob has two options, which I'm going to call Y1 and Y2, the probabilities for his choices. So this is like the probability. Bob chooses up, and the probability, and the other one is a probability. Bob chooses down. Okay. So for example, Alice could be like, oh, I'm going to play 50%, 50%. So half of the time I'll choose up, half of the time I'll choose down. And Bob could be, I'll do 25, 75. So half of the time, a quarter of the time I'll choose up, 75% of the time, three quarters, I'll choose down, right? Now, maybe those are not the best ideal probabilities that each should have chosen, right? Like maybe that's not like the best out, like, the best way to split the ratios. Uh, and so that's what we would like to like analyze, right? Like what would be kind of like in what sense like would be the best way to do it. Uh, so the idea, of course, because this is not like a course in probability, so kind of like skip like some of the stuff, but like if you think about it, um, here like what we're thinking of is that like they're making their choices independent of one another. So like the way Alice's choice is independent from like Bob's choice. Like so what that means, just to make it like more easy to understand, is like if both of them were playing 50% for each choice, right? Like 50% up, 50% down, and same like for both Alice and Bob, that means like like the outcomes of each of those outcomes, potential for outcomes of the game would happen 25% of the time each, because like one half times one half is one quarter. So the idea is that x1, y1, x2, y2, x2, y1, and x1, y2, these four numbers represents like the probability that you would get one of those particular outcomes. Like that, like for example, this is like the probability that Alice would gain, what was this number? So this corresponds to the probability Alice gains uh $5. Because if you look at this matrix, this is like the number 5. Oops. Okay. Is that making sense? Kind of like or like this other one would be like with like the probability that she would win, like she loses $1. So this is like the probability Bob gains $1. Okay. Which again, like it's always useful to think about like the case where everyone is playing 50% of the time, because then like the probability is just, it's like a quarter. In this case, it would be a quarter, a quarter, a quarter, a quarter, right? And if it had been like a 3 by 3 matrix, where like each one had like three outcomes, then it would be 1/9, 1/9, 1/9, and so on, like, for each of them. By the way, there's no restriction. The matrix doesn't have to be a square. So like it is possible, like that for whatever reason, like Bob had more options than Alice to play the game. Like there's no restriction. So what I'm saying is for any size matrix, but I'm kind of like sticking to 2 by 2 matrices to make it more understandable. I just want to show you how the duality appears like coming from linear optimization. That's kind of my goal. So I'm not too particularly like interested in kind of like writing this in the most general way possible. But yeah, like the matrices could be like non-square and everything. Um, so, but so again, from Alice's perspective, okay, whenever you talk about probability theory, like for it to kind of like make sense, you have to imagine that the game is being played a lot of the time, like multiple times, like you're playing the game for multiple rounds. Otherwise, it doesn't make a lot of sense to say, if you're just playing it once, it doesn't make a lot of sense to say, I'm playing it probability one half up or one half down. There's no way to discriminate between the outcomes. So imagine they're playing the game for 10,000 times or 100,000 times or a million times. What would be the optimal strategy for Alice that on average, she would make as much as possible? Because Alice loves large numbers, right? So what Alice would like to do is like for like she would like to choose like numbers probabilities for like on average she would make like the like you know the biggest number possible. So on average, how much is Alice gaining for this matrix? For the matrix we had, it was like -1, 5, you know. So what is the average payoff for Alice? Well, so it would be on average, what does she win? She wins -$1 how many times? X1 times Y1. She wins $5. How many times? In probability, X1, Y2. Then plus $4 times X2, Y1 plus $3 X2, Y2. Okay. So that is like the total amount that Alice makes on average. That makes sense. Now, the cool thing is that this actually can be rewritten in a clever way using matrix multiplication. So this is the same. I think this is like how it should be work. Just to follow the same notation as the book. Yeah, yeah. I mean, it's like not a bad exercise here because everything is being made so concrete with the numbers. But this is the same as this multiplication. So here, like, I'm thinking like just to kind of like at least explain the sizes. If you think of the matrix as 2 by 2, this is 2 by 1. So you can definitely do that multiplication. And then whatever you get would be what? It would be 2 by 1, right? And this is a 1 by 2 matrix, right? So 1 by 2 with 2 by 1 can be made. And this is 1 by 1, which is a number. So if you kind of work it out, you will see that you know, it does agree with like this expression. In fact, like you kind of like see it like because what is going to have like x1 with y1 is going to be this coefficient, and what is going to have x1 with y2, and then well x1 with y2 should be 5, and so on. But I mean, it's not a bad check to see that. So in general, like just to write it more in general, so in general, X transpose times M times Y is represents the average amount that Alice will win. Okay, so it represents the amount of money that Alice wins on average. Okay, is that making sense kind of so far so good? Okay, so now let's look at the game from Alice's point of view again. Okay, so let's analyze this game from Alice's perspective. So the game. So again, when we were like so when we were analyzing the game from Alice's perspective, we were thinking, well, what if Bob chooses column one, or what if Bob chooses column two, right? So the analog of that, the probabilistic analog of that is to say, well, what if Bob chooses, like, with probability y1, column two, column one, and with probability y2, column column two. So here, from her perspective, since everything has been randomized, now you have to assume, we assume that Bob chooses column one with probability y1. But just to I'll emphasize that kind of like you're thinking that the probability has been fixed. So I'll just kind of put like a B to specify that I'm not considering that as a variable. Just like I'm just pretending, okay, what if that number happened to be 25% or whatever the number is? And column two. Okay, now I'm realizing that probably I shouldn't ask this on the exam because it's but so just sit and relax because I'll just tell you how everything works, but it is kind of too much, like I think, to set it up properly on the exam. But I do want you to kind of get like a feeling for how the duality appears. So kind of more like so this class has become more like an appreciation class, just so that you see where it comes from, the duality. But like, yeah, it would like, and also it uses probability theory, so maybe it's a little bit unfair to put it on the exam. But okay, but so again, so just we're pretend I'm Alice. I'm pretending that I'm saying, oh, Bob is going to play the game with these probabilities. Like somehow like I pretend that I know those values. So from my perspective, what should I try to find? I'm trying to find which probabilities I should use to maximize my average gain, right? Like my payoff. So Alice would like to maximize her payoff, right? Which is kind of what we were doing before, just to go back there for a second. Um, that if, this is what we were doing before. Like we would say, well, what if Bob chooses column one? Then I would choose the highest number. What if Bob chooses column two? Then I would choose the largest number, right? Available in that column. So I'm doing the same here. It's just that now since Bob is playing with the game with certain probabilities, um, I cannot um I have to choose like my probability so that my average value is the best possible. So what Alice wants to do is solve a linear optimization problem. That's what I'm trying to get at. So what is Alice trying to do? She's trying to find the max of what? Of her average gain. Where was the average gain here? It was this one. Oops. This is what Alice is trying to solve. Actually, let me write it a bit better. Sorry about that. I can need a little bit more space. I'll write it downstairs here. Well, I think at least I could, no, I think at least I could ask you to set this problem up. I think that's fair. Like, so just set it up, nothing else. Like, just to make sure you recognize the variables. I think that that would be okay to ask on the exam. So yeah, I'll give you like a matrix and then I'll ask you what would be the problem that Alice wants to solve, like the linear optimization problem, just to know that at least you know how to set it up. So so she's trying to maximize her average gain where the variables are non-negative, right? Because probabilities are non-negative numbers where and what is a condition that probabilities should satisfy? Probabilities have to add up to one, right? So you cannot play more than 100%, you know, so like probabilities cannot go over 100%. So in fact, you can kind of rewrite this a little bit better as a max problem where this is what? This is a max of what? As a vector. I just want you to see it as a vector. So it would be, uh, oh yeah, perfect. Y2b minus y1 yb, comma, then the other one would be 4. Oh no, that's just 5. Oh yeah, yeah, yeah. No, I'll do it. Sorry. Like I'll do it like yes, yes, yes. Oh yeah, if you do the dot product, you'll see that this gives you minus y1 plus 5 y2, comma 4y1 plus 3y2. So this is like a, you know, this is what we usually were calling the vector x. Okay, and the matrix here would be 1, 1 times x1, x2 equals 1. So this is like the matrix A in this case. I mean, it's a very simple linear optimization problem because it only has one constraint, right? Usually the matrix is gigantic, like, well, has more rows. Like this one only has one row. It's a matrix with one row because there's only one condition, which is like that the probabilities add up to 1. Okay. So yeah, something like this, I feel like I could ask you to like just write down, like, you know, what is like the, you know, the linear optimization problem like Alice will try to solve or something like that. Um, but you see, it does have like the similar shape that we have discussed before because it's a max, the variables are non-negative, the variables, well, in this case, add up to 1, which like is not necessarily like a requirement that we had before, but it's just because it's like a probability vector. And and then the idea is that, okay, so this is what Alice would try to find if she, let's call this A for like Alice. So let's call this A of Y because this is what Alice is trying to do if Bob chooses this vector, this probability vector. And then what is like the worst case scenario for Alice? The worst case scenario for Alice, because we had talked about that before. The worst case scenario for Alice would be the scenario where she gains the least amount possible. So the worst case scenario for Alice is found by considering the minimum value that AY takes. By the way, this is the matrix MY. So if you don't specify things, like this is kind of like a mean, I'll just kind of like drop like all these like constraints so that we just focus on what we're trying to, like what the function is. It's kind of like the mean of like the function, but the mean that we're trying to find is kind of like this max of these two things. So this is what people sometimes call like a mean max, if you have seen that notation before. Okay, I'm almost there to the punchline, I promise. And then how does the game look from Bob's perspective? So from Bob's perspective, what is his goal? Bob's goal is to make Alice gain on average as little as possible, right? Like Bob loves negative numbers, so he wants Alice's payoff to be as little as possible. So if the idea is that if Alice chooses to play the game with probability X, probability vector X, then Bob is trying to minimize her gain. Bob tries to minimize her average payoff. So what is Bob trying to solve? Bob is trying to solve the minimum of like the average payoff. So it's the same function like as before. Like let me put it here. Yeah, so I would just ask you to maybe like set up like these linear optimization problems. I wouldn't like ask you anything else. By the way, I'll send you the study guide tomorrow. That way I kind of specify what I expect you to know how to do, and I'll kind of put like an example in the study guide so that it's clear what I'm asking for, but it would be just kind of to write these linear optimization problems. And so, but now again, now Bob is trying to minimize the average gain of Alice, and so he's trying to choose the probabilities for him. So now the variables are y1 and y2, because that is what Bob is trying to find. And the condition is the probability should add up to 1. Okay. But again, this is literally like an optimization problem, like the ones that we have uh, written before. It's just that here, if you kind of write it in the vector notation as before, this would be a minimum of what? Now it's y1, y2 dot let's see, minus x1 plus 4x2, 5x1 plus 3x2. This is what the dot product can be rewritten. That can be rewritten as a dot product. And then so this is like the vector y. So the restrictions is that y is non-negative, and that 1, 1 times y1, y2 equals 1. And so this is like the matrix A for this optimization problem. And then this is like y. And so let's call this bx because this is what Bob is trying to do if Alice chooses x, the vector x. Okay, and then what is the worst case scenario for Bob? The worst case scenario for Bob is one where of all these possible outcomes, she makes the most money on average. Because again, Bob hates large numbers. So the worst case scenario for Bob is the largest of all of these numbers. So the worst case scenario for Bob is the max of all of these, not all of these like values. But if this is not a multiplication, this is kind of like an indexing. But this is like a max. What is bx? It comes from this function, which is a mean between y and m transpose dot x. Like if you work it out, like it kind of like ends up becoming this. So one is, and this is called like a max mean, because it's a max of a mean, you're looking for the max of the minimums. And kind of like, if you look at it in this notation, it's kind of like interesting because here this uses the matrix transposed and the original one uses the matrix M. So essentially, like, and this is kind of like, I don't think I would have enough, I honestly wouldn't have enough time to kind of like, go over it now, and so I will, like that's fine. Like I won't. But the idea is that there is a way to see that this would be the dual in the sense of the duality of these linear programs that we have talked, linear optimization problems, where like you can show, and the book does do like a good job describing that. If you're curious about it, you can kind of like rephrase the problem so that one is literally the dual of the other, and if they are the duals of one another, the value that maximizes it is the same as the value that minimizes it. So that means that you can play the game so that on average, like like their strategies agree on what the payoff should be. Like so. Like long story short, because like it does require a bit more details than what I'm saying. Long story short, um, one can show one problem is the dual of the other in the sense of duality that we have been discussing. One problem is the dual of the other. And if you remember the duality theorem said that the max of the optimization function is the minimum of the other function. So that boils down to saying that these two have the same value. So so that means that the both if they play the game randomly, they like the optimals, like the worst case scenario for both of them have like the give the same payoff matrix, like or the same value average value. So and this is called like the von Neumann mean max theorem. Um, so let me put here opt for optimal. So of the optimal like there's an optimal choice of probability vectors for both Alice and Bob, and for those optimal choices, like the worst case scenarios, like agree. So there's an optimal choice of probability factors for Alice and Bob, and for these choices, the payoff, like the worst case scenarios are the same. And it is like a really cool thing to like, if you go through all the details in the book, it is kind of cool to see how it really becomes a dual of the other problem. In fact, there's something else that you can do, which is kind of more interesting, that any optimization problem can be written as a game, as a game, like one of these games, like a zero-sum game. So there's kind of like a converse, and then the duality theorem is like a consequence of this min-max result. So like, this can be proved without knowing linear optimization. And that's how it was proved before. Like von Neumann was like a very famous mathematician. He proved it before, but once he learned about this linear optimization stuff, he was, oh yeah, so my min-max theorem is just like the duality from linear optimization. Um, but yeah, so here what I did was like I started with the matrix game and I constructed a linear optimization problem. But what I'm saying is that you can kind of go in reverse. So if I hand you a linear optimization problem, you can kind of like associate to it a matrix game. So kind of like it goes both ways. But of course, that's not the interest that we would have. But again, so what I would do, like, yeah, I think just to keep it simple, um, what I would do for the exam is that, it's like I would give you like a matrix like this, something like this, and I'll be like, okay, if Bob plays a game with probabilities y1 and y2, for example, what is the optimization problem that Alice would try to solve, so that you kind of, and then you would end up writing like something like this. So it's kind of just more like recognizing how to set it up that I would like you to know how to do, because at least that kind of shows you that that's connected to the stuff we have been doing. But again, I'll write that carefully on the notes that I send you tomorrow so that you know what I mean by that. So I would just ask you from like the matrix, write me the optimization problems that Bob and Alice are both interested in solving. Okay, so that's simple enough. Um, Yes, so I think this is a good place to end. So as I said, next time on Monday, I'll just like answer whatever questions you have. But yeah, there's no more material for the exam. So the exam won't have like, it's not computational at all. I think there are very little computations because I'm not asking you to solve anything with the simplex method. It's a lot more like setting things up, write the dual of this problem, or like, it's a lot of like, just write me like the problems that you would have solved if you wanted to use the simplex method. Once we get back to the final, I will ask things again that require using the simplex method, but it is more like about setting things up this time around. So just keep, so it would be probably will have more problems than like, it would be kind of more like similar to the first one where there were like what 5 or 6 problems, because they I'm not asking, there won't be much that you have to solve. It's more like writing the systems of equations for the most part. So yeah, but yeah, let's finish here. Oh, sorry, did I go? Is there anyone needs like to see their notes or okay? So
Okay.